Welcome to this. This is our 13th lecture in the course on fundamentals of transport processes. In the previous 6 hours of lectures, I have tried to give you some idea of what is it that we are trying to study by going through the process of using dimensional analysis to derive correlations and then trying to give you a physical understanding of what those correlations mean, okay, in terms of the ratios of convection and diffusion. If you recall, in the last lecture I had said that convection is the process by which the fluid carries along with it, okay, whatever mass is dissolved in it, whatever thermal energy it has, or whatever momentum it has with it. Okay. And the flux due to convection across a surface is just given by the product of, in the case of mass flux, the concentration times the velocity, in the case of heat flux, the energy density times the velocity. Okay. So, we can have a unified description of the fluxes of mass, momentum and energy. Okay. Similarly, I had also described for you the process of diffusion. Diffusion takes place whenever there is a gradient, a variation in the concentration, the energy or the momentum. Okay. And the flux, okay, which is the rate of transport, okay, per unit area, per unit time, okay, is a flux. It can be written as a diffusion coefficient times the difference in the density of the whatever is diffusing, okay, the density of mass, the density of momentum or the density of energy, okay, divided by a length, the cross stream or the length across which there is the variation. Okay. So, therefore, these diffusion laws can be written in a unified framework: Fick's law for diffusion, Fourier's law for heat conduction, Newton's law for viscosity. The flux is equal to a diffusion coefficient times a difference in density divided by a length, or a diffusion coefficient times a gradient in the density, okay, change in density divided by length, whether the density is that of mass, momentum or energy. And from these we get the diffusion coefficients: the mass diffusion coefficient for mass, the thermal diffusion coefficient for energy, which is written as K by rho Cp, the momentum diffusion coefficient for momentum, which is the ratio of the dynamic viscosity and the density. So, these are the 3 diffusion coefficients. All 3 of them have dimensions of length square per unit time. Okay. Dimensionless numbers can be broadly written as dimensionless fluxes, mass, momentum and heat fluxes. The mass flux is the Sherwood number, the heat flux is the Nusselt number. Momentum flux is non-dimensionalized differently conventionally in comparison to mass and heat flux, whereas mass and heat flux are non-dimensionalized by the diffusive non-dimensionalization, the ratio of the flux and the right side of the constitutive relations d delta c by L or k delta t by L. The momentum flux is traditionally scaled by the kinetic energy density. It is scaled by inertial scales rather than by viscous scales, okay, whereas mass and heat are scaled by the diffusive scales. Okay. That is the way that the momentum flux is traditionally defined. There are ratios of convection and diffusion, the Peclet number for mass and heat transfer and the Reynolds number, and then there are ratios of diffusivities. Momentum by mass is the Schmidt number, momentum by heat is the Prandtl number. Okay. So, these are the broad categories of dimensionless numbers, and all the correlations that we have derived can be written in terms of these dimensionless numbers. If you recall, we derived a correlation for the heat transfer in which the dependent dimensionless number, the dimensionless flux, has been written as a function of the Reynolds number and the Prandtl number. Okay. Similar is the case for other such problems. We saw for a falling film problem, we have the Reynolds number and the Prandtl number to a different power. Okay. The Nusselt number is equal to the Reynolds number times the Prandtl number to a different power. Similarly, in diffusion dominated regime, okay, the Peclet numbers are small or the Reynolds numbers are small. In that case, inertia should not matter, and therefore, the Nusselt and the Schmidt numbers tend to a constant. Then there is a third regime of a turbulent flow, okay, where the dimensionless numbers are a lot more complicated. And we also talked about natural convection. Okay. In this case, the velocity is determined from the force density exerted due to the temperature difference due to a heated object, okay. And therefore, the dimensionless flux is defined the same way as we had earlier. However, in our expressions for the ratio of convection and diffusion, the convection velocity is not specified. Okay. It is not, you do not have fluid that is being forced past the object at a specific velocity. The velocity itself is generated due to the temperature difference, and therefore, you need to calculate a velocity scale, okay, based upon a balance between the buoyancy force density due to the temperature difference and the inertial force density, and then use this velocity in order to define dimensionless numbers. And we saw the dimensionless numbers that emerge, the Grashof number or the Rayleigh number. These are Reynolds numbers, and the Grashof number is the square of a Reynolds number based upon the convection velocity, based upon a balance between the force density and fluid inertia. And the Rayleigh number, instead of the nu square in the denominator, you substitute that with the product of the kinematic viscosity and the thermal diffusivity. And we had seen once again there are certain correlations that arise in this case. The program for the rest of this course is going to be able to solve the entire problem analytically in order to have a physical understanding of how these correlations arise. What is the difference whether the Reynolds number is large or small, or the Peclet number is large or small, okay? And why do different regimes as well as different conditions at the surface of objects, why do these give rise to different kinds of correlations? Okay. So, how do we treat the problem? The first thing we do is a continuum That is, we assume that the temperature, the concentration or the velocity fields are continuum fields. Okay. That is, if you are analyzing some object, okay, in some coordinate system, okay, we assume that this temperature is continuously varying as a function of position, okay, the temperature, the concentration or the velocity. These are continuously varying functions of position, that is, they are defined at each and every point within the flow. Okay. So, that is a continuum approximation for the velocity, the concentration or the temperature fields. Okay. These continuum fields are defined within fluids. Okay. In this course, we will be dealing primarily with fluids. Okay. The difference between solids and fluids is, of course, that for a solid, if you apply some kind of a stress, okay, it will deform for some, okay, extent, and then it will stop. Okay. If you apply under continuous application of a stress, provided that stress is small enough that it does not break the solid, it is going to deform to some extent and then stop. Okay. So, therefore, in a solid, an applied stress generates a strain field. Whereas, to a fluid, if you apply a stress, there is a continuous velocity. Okay. As long as stress is applied, the fluid will continue to flow. Okay. It will not stop as long as the stress is applied. Of course, if you remove the stress, then it will come to a rest. Okay. So, fluid deformed continuously under applied stress. Okay, so, this is a solid, this is a fluid. Okay. at the microscopic level, at the molecular picture, the difference arises because in solids molecules have fixed equilibrium positions. Okay. They have a fixed crystal lattice, okay, or at least crystalline solids will have a fixed crystal lattice, okay, within which all the molecules are sitting, okay, within the potential well that is created by their neighbors. Okay. So, there is a fixed lattice, and therefore, if you deform this lattice a little bit, if you apply a stress, okay, all the molecules will shift a little bit, okay, from their equilibrium positions, okay, and that shift of the molecules exerts a restoring force, because molecules would prefer to come back to their equilibrium locations. So, that shift of the molecules from their equilibrium locations generates a restoring force, and that causes a stress. Okay. So, this happens because the molecules have defined locations within a solid. There is of course diffusion in solids. Okay, it takes place by two means. One is the interstitial diffusion due to molecules which are imperfectly located within the interstitial space of the solids, and the other is due to vacancy migrations. Certain locations may not be filled with a molecule. Okay. So, if you have a vacancy within a solid at some location, okay, you could have another molecule move in, okay, and consequently the vacancy actually migrates the other way, okay, in a solid. So, you do have processes of diffusion in solids as well due to either interstitial or vacancy diffusion, but these are extremely slow processes. Okay. These processes takes place over extremely long time scales, over many years, and therefore, diffusion over reasonable time scales required for material transformations does not really take place in solids. In fluids, on the other hand, the molecules do not have equilibrium positions, okay, and therefore, they are free to move about in any direction. Okay. And therefore, in a fluid, if you apply a stress, okay, the molecules will move continuously in response to that stress. They do not have equilibrium positions, okay, and because of that, the molecules move in such a way as to accommodate that stress and thereby generate a fluid flow. Okay. So, the fluid flow is continuous in liquids and gases, in all fluids, okay, and that is a fundamental difference. Okay. The reason that most of these transfer processes are carried out in fluids is for this reason, because of the molecular motion of the molecules in a fluid, these transport rates are much higher. There are molecular motions in solids as well. Okay. In all cases, the root mean square velocity is given by root of 3 kT by m, the thermal energy. Okay. However, in the case of solids, this motion takes place about defined or specified locations on a lattice, and therefore, that when you apply stress on a solid, it will deform to some extent and then it will stop when the restoring forces become equal to the applied stress. In a fluid, on the other hand, the molecules can freely move about anywhere within the system, because they already have thermal fluctuating velocities. Okay. And because the molecules in this fluid are agitated and they do not have equilibrium positions, any applied stress is going to generate a flow which will accommodate the applied stress, and if the stress is continuous, the flow will be continuous. We will deal exclusively with fluids in this entire course. Okay. Fluids, of course, are comprised of liquids and gases. Okay. The distinction between liquids and gases at the molecular level is clear, but at the continuum level, okay, they are not distinct. Okay. At the molecular level, in a gas, okay, the separation between molecules is much larger than the molecular diameter. Okay. The molecules are once again in a random state of fluctuations due to the thermal energy, but the distance between molecules is much larger than the molecular diameter, okay, typically about 10 to 100 times. And for this reason, the interaction between molecules in gas can be considered as a series of instantaneous collisions between pairs of molecules, okay, followed by the range of interaction is much smaller than the distance between interactions. Therefore, these can be considered as a series of instantaneous collisions between molecules in a gas. Okay. For most of the time, each molecule is out of range of the interaction with any other molecule, but there are brief occasions on which an interaction takes place, and this scatters the velocities of the molecules. In between such collisions, the molecules follow a straight line path, okay, or a ballistic path in case there is an applied force. Okay. In liquids, on the other hand, the molecules are all located at distances which are comparable to the molecular diameter. Okay. Effectively, in liquids, okay, if you draw the interaction potential between molecules, okay, the interaction potential between as a distance between two molecules. Okay, let me call this as R to distinguish it from the molecular diameter. Okay. For very short distances, there is a repulsive part, and then at long distances there is an attraction, okay, and then as you go further away, the force comes down to 0. Okay. This is a typical potential versus distance curve for molecules. Okay. In the case of liquid molecules, okay, each molecule is close to the potential minimum of the neighboring molecules. So, the distance is comparable to the molecular diameter itself. Okay. So, that is the fundamental difference. Okay. If a molecule has to move some distance within a liquid, the other molecules have to move out, okay, out of the way. So, the interaction is continuous and it is multi-body, okay, simultaneous interaction between many molecules. At the molecular level, this is the difference. At the macroscopic level, the difference is not actually that much. Okay. At the macroscopic level, the fundamental laws, the constitutive relations, whether it is Fick's law, okay, okay, or Fourier's law of heat conduction, or it is Newton's law of viscosity. Okay. These laws are applicable both to liquids as well as gases. The laws are identical. Okay. Therefore, as far as calculations are concerned, we can use the same equations whether it is a liquid or a gas. The only difference is that between liquids and gases, these coefficients change. Okay. The diffusion coefficient, the thermal conduction coefficient, and the viscosity coefficient, these coefficients are different depending upon whether it is a liquid or a gas. However, the constitutive relations themselves are identical, independent of whether we are dealing with a liquid or a gas, so long as it is a fluid. Okay. So, we can deal with both of these on equal footing, and during the course itself, we shall really make no distinction about whether the system we are considering is actually a liquid or a gas. Okay. So, we will deal exclusively with fluids in this course, and the description itself does not distinguish between liquids and gases. The only difference arises when we have to write down the diffusion coefficients. These turn out to be, the numerical values of these turn out to be very different depending upon whether it is a liquid or a gas. And we will look a little later at how do we derive these constitutive relations and the diffusion coefficients. Okay. So, I said in this course we will be dealing with fields. Okay. These are continuously varying position, functions of position. Okay. The concentration field, for example, it is in general a function of all three coordinates as well as time. Okay. It is defined at each location within the flow. Similarly, the temperature field or the velocity field. The only difference is the velocity itself is a vector. So, because of that, the velocity field has a vector character, but however, it is a field. That means that the value of this concentration, temperature or velocity is defined. Okay. It is a single valued function. It has a unique value at each position, okay, within whatever system that we are analyzing. Okay. Now, how do we get the concentration field locally at each point within the flow? What does it mean? Okay. So, let us look at the concentration field for simplicity. Okay. What it means is that, let us say I have the concentration of some species, okay, within the flow. Okay. The concentration of some species within the flow, okay, is written as the total mass of that species. Okay. Let us say species I. Okay. Let us say you have a multi-component system with many species with many different types of molecules in there. The concentration of species I is equal to the mass, total mass of species I divided by the volume, okay, where delta V is this volume, in the limit as the volume goes to 0. Okay. So, the idea is that if I want to know the concentration at a particular location, okay, I go to that location and consider a small differential volume about that location, okay, and find out what is the total mass of all the molecules of species I within that volume. Okay. Divide that by the volume itself and I get a value for this concentration. Okay. If this volume is large, then of course, the concentration will depend upon the size of the volume and the location. However, in the limit as the volume goes to 0, okay, as delta V goes to 0, the mass within that volume also goes to 0 in such a way that the ratio of the two approaches a constant value. Okay. That is the value of the concentration at that location. Okay. So, in order to get the concentration of species I, what I need to do is take the limit as delta V goes to 0 of the number of molecules of species I times the molecular mass of species I, okay, divided by delta V, okay, where capital M I is the molecular mass of species I. Okay. So, that is the definition of the concentration. Okay. In the limit, as if you go to a point and take a small volume around that point, it can be of arbitrary shape, arbitrary size, but as the volume goes to 0, as you shrink it further and further, find out the total mass within that volume divided by the volume itself. The concentration is the ratio of the mass to the total volume. Okay. I can define the density, okay, the total density, okay, is equal to the total mass, okay, of everything put together, okay, divided by the volume in the limit as delta V goes to 0. Okay. So, this is going to be equal to summation over all species of number density of each species times the molecular mass of each species, okay, divided by delta V. So, it is the total mass per unit volume. The density is of course, the sum of the concentrations of each species within this volume if you had a multi-component system. Okay. If you had just a single component, the mass and the concentration and the density will be the same. Okay. Now, for heat transfer, we have to define the temperature field. Okay. Note that this is a function of position, it could also be a function of time. Okay. And once again, this is defined through the energy density. Okay. The energy density at a location is going to be equal to the total energy due to all of the molecules. Okay. Okay. N C okay, divided by the delta V limit as delta V goes to 0. Okay. This is the internal energy if I use specific heat at constant volume. If I use specific heat at constant pressure, that would turn out to be the enthalpy of the system. Okay. So, what you do is you take the total mass within the system, the specific heat at constant volume times the temperature divided by delta V, that is the energy density within the system. Okay. And of course, if you had multiple species at equilibrium, the temperatures of all of these have to be equal to the same. Okay. This is actually equal to the limit as delta V goes to 0 of the total internal energy, okay, the total internal energy within this volume divided by delta V. Okay. So, we will take the internal energy of each of these molecules and divide by delta V. Okay. If you had a monatomic gas, for example, the internal energy would be just due to the translational degrees of freedom itself. If you had diatomic molecules, you will have a rotational degree of freedom as well, and for polyatomic molecules you will have vibrational degrees as well, if there are excited vibrated states at room temperature. Okay. So, I take the total energy density within that volume, and from that I will find out what the temperature. Okay. So, the temperature locally, okay, E, I can write it as rho Cv times T, okay, which is the summation, okay, limit as delta V goes to 0, okay, of the total energy, internal energy within this volume divided by delta V. Okay. And as I said, this internal energy is in general okay, n Cv times, okay. If you had just translational degrees of freedom, this will just be equal to half m into C square, okay, for each molecule. Okay. Okay. That will be the total energy, and that has to be equal to equated to rho Cv times T to get what is the temperature. Okay. So, therefore, from the internal energy, equating it to rho Cv times T, you can find out what is the temperature. So, this basically defines the temperature field. The temperature field is defined from the internal energy field or the enthalpy field, okay, by taking into account the total internal energy of all the molecules within a volume, dividing it by the volume itself. Okay. In the limit, as the volume goes to 0, the number of molecules also goes to 0. Therefore, the internal energy also goes to 0. But the ratio of the total energy within that volume divided by the volume itself, that will tend towards a constant value, and that is the internal energy density. And from the internal energy density, you write it as the mass density times Cv times the temperature, and from that you can define what is the temperature field. So, the fundamental variable in this case is actually the internal energy density or the enthalpy density, depending upon whether you choose working at constant volume or constant pressure. Okay. Now, you can also define the momentum density. Okay. Okay. The momentum density is in general defined by taking the total momentum within a volume and dividing it by the volume itself. Okay. So, I take summation, okay, of the mass of each molecule times the vector velocity of each molecule. Okay. So, within this differential volume, each molecule has a velocity vector. So, therefore, for molecule I, let me call it by a different symbol here. Okay. For each molecule J has a velocity which is equal to vector J. Okay. It has 3 components, x, y and z components. So, it is a vector. I can write Vj as is written as Vx j times Ex plus Vy j Ey. Okay, it has 3 components, where Ex, Ey and Ez are the unit vectors in the x, y and z direction. So, therefore, this is a vector. So, I take the total momentum, the mass times the velocity of each molecule, and then divide that by the volume and take the limit as delta V goes to 0. Okay. So, that is the momentum density, okay, and the fluid average velocity is defined as the mass density times the mean velocity of the fluid is equal to the momentum density. So, that is the definition of the momentum density and the definition of the mean velocity. So, the mean velocity is defined through the momentum density. So, the fundamental quantity here is the momentum density itself. I equate rho times u, mass density times the mean velocity, to the momentum density, and from that I get what is the velocity vector. Okay. Where once again the momentum density, in order to calculate that, you go to a point, construct a small volume around it, look at the total momentum of all the molecules within that volume, divided by the volume itself. In the limit as the volume goes to 0, this momentum density tends to a constant value, and that is the mean velocity of the fluid at that location. And these fields are specified at every location within the flow, and they have a continuous variation, okay, with location within the flow. Okay. So, these are the quantities that we will be writing down equations for, okay, the fundamental quantities, the densities, mass density, the temperature through the energy density, and the mean velocity through the momentum density. As far as momentum density is concerned, note that we are adding up the vector velocities. So, if the molecules have random velocities in such a way that the sum of the vector of all those velocities is equal to 0, that means that the fluid velocity is equal to 0, or the fluid is at rest. So, the fluid being at rest implies that the average velocity is 0. It does not mean that the molecular velocity is 0. Even when a fluid is at rest, all the molecules have their own random fluctuating velocities. The point is that the sum of all of those velocities, the vector velocities, is equal to 0. Okay. Similarly, if a fluid is moving, the sum of all those velocities is equal to the mean velocity of the fluid. It is not the molecular velocity. The molecular velocity is actually much faster. The fluid molecules typically move at a velocity comparable to the speed of sound, and whereas the mean velocity of fluids in most common applications is actually much less. Okay, it is much less than the speed of sound. Therefore, the fluid velocity, which is the vector sum of all the molecular velocities, is usually much smaller than the molecular velocity itself. So, even when the fluid is at rest, it does not mean that the molecules are stationary. The molecules are in a state of constant motion, and it is this motion that gives rise to diffusive transport. Okay. Similarly, the thermal energy of the molecules in the fluid is non-zero even when the fluid is at rest, and that is the reason why the molecules have a non-zero temperature. Okay. The thermal energy is given by the velocity fluctuations about the mean velocity. So, the mean velocity enters only into the momentum density. The thermal energy contains only the fluctuating velocities, which is the difference between the molecular velocity and the mean velocity. Okay. So, that is the distinction between the thermal energy and the kinetic energy of the fluid. Kinetic energy of the fluid, as defined, the mechanical kinetic energy, is based upon the fluid mean velocity, whereas the temperature, the thermal energy, is based upon the fluctuating velocities of the molecules. That is the distinction. Okay. So, what do these fields actually mean, and how do we go about writing down equations for these fields? Okay. I will try to give you a little more insight into that when we continue this discussion in the next lecture. Okay. So, I will see you then.